So to start, I want to do a brief recap of what we learned, hopefully, last week. So we talked about transactions. It's about bundling several SQL statements into an atomic unit. And we had this shortcut in terms of read and write operations. Yeah, I wrote R or W on a specific data object as a short form of, yeah, there's an insert statement, there's a delete statement, there's an update statement. So at the end of the day, what we're discussing is having multiple SQL statements that are bundled in a transaction. And how do you do a transaction? You write begin, then you send your commands, your SQL statements, and then you eventually write commit. And then there are two options. Either the database tells you, yeah, fine, I committed it, or it tells you, no, I couldn't commit that. I didn't do any of the stuff you sent me as part of the transaction. And that brought us to these ACID principles. And all of them are super important. A, like atomicity, meaning all or nothing. All of the actions of the transactions are performed, in particular the change operations. Yeah, if a transaction only reads stuff, yeah, that's not so critical, but it gets interesting if a transaction changes things. And A means all changes are performed or none of the changes are performed, but not in the middle. Huh? We had this example with a bank where just $100 is removed from one account, but not from the other. So the bank wins, or the other way around, the customer wins. That mustn't happen. Huh? All or nothing. Consistency means that the transaction leaves the database in a consistent state. The transaction leaves the database in a consistent state, meaning while doing the transaction, you can do whatever you want. You can violate any consistency, not any, but it's more complex in reality, but from a theoretical point of view, you can violate those constraints. Just when you commit, you must make sure that the constraints are fulfilled again. The database system will help you in checking that. And if you violate any of those consistency constraints, the transaction will not go through, it will not commit. Consistency constraints are foreign key constraints, and anything like, okay, a lecturer can only must give 2 lectures, and at most 5 or something like that. Those are consistency constraints. Or we had that with a banking example. If you transfer money from one account to another within a bank, the sum over all accounts must be the same before and after the transaction. Otherwise, you lost money or you generated money. That's a consistency constraint. Maybe a footnote, why is it more complex in reality? If you violate a key constraint in a single statement, you will already get an error. If you can't violate a primary key constraint, unique constraint, stuff like that, the database system will immediately tell you, no, that's not going to work. So it's a mix. Then the I for isolation means that from the point of view of any transaction, it looks like you own the database. You don't see ongoing actions of concurrent transactions. So we had this example with Mensa. You go into Mensa, it looks like the Mensa, you own Mensa, you're the only student in Mensa, but in reality you have like 3D glasses on, and it looks like there's no one else there, whereas the Mensa is actually crowded and stuffed with people. The same with noise cancelling headphones, you don't hear anything, whereas it's really loud there. Yeah? And that's pretending that you own the database. Then there's a D for durability, meaning once the transaction commits and the database signals, yeah, I committed it, the database must never forget that change. So the change you apply to the database must not be lost, no matter what. And we learned that 100% durability is impossible. I gave you the Star Wars example with a Death Star destroying a planet. Nothing is durable on that planet anymore, obviously. So durability cannot be 100%. It's always a compromise. It's always, you can have better durability, but there's no such thing as perfect durability. The important thing is when you link these transactions back to ACID, for our transactions, we're looking at the ACID properties must be guaranteed by the system. That's very important. And that is what the art of database systems is about, or parts of it. So how do we do that? How do we guarantee automatic isolation? That was a focus of last week and also this week. So we're focusing on the I, the letter I on isolation. So there are other classes of algorithms like durability. We learn more about that in the core lecture. Consistency is more like a side effect. Atomicity it's a bit part of this lecture, but also a part of the core lecture. Yeah, and then we had to introduce a lot of terminology, including a schedule, also sometimes called a history in German. It's called a Historie, very misleading term to my understanding, because all it does is it specifies how the single actions of those operations are interleaved. Yeah? Single actions being a read operation on a data object, a read operation on a write object. So you have two transactions. Yeah, you can, if that's one transaction, that's the other transaction. You can read, first execute. Yeah? You have 5 operations, 1, 2, 3, 4, 5. That's the transaction. 1, 2, 3, 4, 5. That's another transaction. You can first execute those. You can first execute those. That's called a serial schedule. But of course, to increase efficiency and have something really going on concurrently, you interleave those actions somehow. Yeah? And then the question is, how exactly can you interleave those actions without ruining the database state? Yeah? Without still preserving isolation, still making sure that both of my hands believe, I own the database alone. Yeah? There's nothing that is a side effect of running transactions concurrently. That mustn't happen. There's no such thing as a lost update, race condition, stuff like that. That must not happen. The database must make sure that it looks like as if they were executed alone or in a serial fashion. Yeah, so a schedule defines that concrete interleaving of read and write operations. And then we make arguments along schedules. So I write down schedules on a slide, and then we argue, oh, is it good, is it bad, la 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 la. But you could also implement that algorithmically, actually. So there's systems doing that. They create these schedules. Yeah, they have a bunch of transactions. They create a schedule, and then they reason about whether that schedule is correct or not. However, keep in mind that's not the standard way of doing it, because that's also what we learned last time. There's batch versus operation at a time. Typically, it's more like you have 100 people sending requests to a database system, and for each of those requests, the database system must directly decide, is it good or is it bad? Am I allowed to execute that, yes or no? That's not that you get all the transactions, and then at the end of the day, you can come up with a fantastic schedule. That's not how it works. Yeah? So you have to do it on the fly directly, and that makes it more demanding. Serial schedule, meaning transactions are executed one after the other. Serial schedule. Yeah, first this hand, then that hand, or the other way around. If there were a third hand, yeah. Serial schedule. Schedule one transaction after the other. Conflict serializable schedule. So we define these conflict operations. So basically operations from two transactions on the same data object where at least one is a write operation. Those were the 3 conditions. Yeah? One read, one write, same data object A, and from different transactions. Yeah? Transaction 1, transaction 2. Those are conflict operations. And then basically for every schedule, if you want to decide whether that is conflict serializable, you can swap all operations except the conflict operations. That's not allowed. And if you can swap those operations in a way that you end up with a serial schedule, you showed that it is conflict serializable. And that's what we did on the slides. And that is a powerful tool to decide whether any given schedule is conflict serializable. Yeah, then we also talked about the conflict graph. That's an aggregated form of a schedule. In a schedule is also a graph. But the nodes are the atomic actions, read and write operations. Yeah? And then there are arrows in between that define the order which comes first. The conflict graph is an aggregated form. In the conflict graph, the nodes are not individual operations, but transactions. One node for each transaction. Yeah, and then you basically you can derive the conflict graph from any schedule. Yeah, then there's another important property of these graphs that tells us if there's no cycle in the conflict graph, the associated schedule is conflict serializable. Yeah, that is what we looked at last week, and now we continue on that this week a little bit. Not sure whether I go into the notebook, but if you're interested, so we have a notebook where you can play a little bit with the transactions. So you, in Python directly, you connect to a database. We use DuckDB for the example. And then basically you can signal, I start a transaction 1 with a begin. Then you, so basically you do 2 connections here to simulate 2 transactions. Yeah, and then you start a transaction calling begin on connection 1. You send a couple of statements there. And you can also send statements to connection 2 and so forth, and then you can play with what's going on when you send transactions to database. It's a very practical notebook, actually. Okay, so here's the agenda for today. So there are a couple of isolation problems we want to look at and want to look at their solutions. So the most basic problems are dirty read, non-repeatable read, and cascading rollback. Yeah, and based on that, we will look then for a couple of other solutions. But just to give you an idea on what's going on, if you're in this space, this is really how it feels like. So whenever you solve one problem, then you feel like, oh, there are 3 other problems that I created. Yeah, you cut off one head of the dragon, and 3 other heads will grow, and oh my gosh, it's like an endless story. Feels like in between, but eventually you will get there. Yeah? Just to give you an idea. So it's not an easy topic. It's also, actually, it's every time I have to teach concurrency control and prepare the slides, I complain with my PhD students. Yeah, also this morning again, I say, oh, this is so laden by, there's so much historic stuff. Yeah, I look at it and it feels like punch cards. It feels like there's so much dust, and looking at the topic, I first have to blow away the dust, like, yeah, and then, oh, it's a punch card. Maybe punch cards were fine in the 70s, but not in 2024 anymore. Yeah? So that's a bit how this topic feels like, yeah? From the point of view of 2024. So there are many more clever, more interesting algorithms you can do. Again, sorry for the cliffhanger. That's more for the core lecture. Also, we have some research topics going on there for thesis work. The problem is you have to be aware of these things when working with a system because they're very generic. And the stuff I'm explaining not only shows up in databases, but also operating systems, for instance. Operating systems and database systems obviously have a huge overlap. And the mechanisms you find in operating systems, but also in distributed systems, are very similar to what I will be explaining today. The same problems and same solutions sometimes. They're not always the same. Of course, the database systems have the best solutions. Yeah, it's clear. What do you expect? But yeah, okay. So let's look at the terms. So what is a dirty read? We use dirty read to refer to reading a value by a transaction that was written by another uncommitted or aborted transaction. That means that a value was read that in terms of isolation shouldn't have been visible to other transactions. You have to think about what isolation implies. It means that, okay, if some other transaction does something, you're in Mensa, there is some student eating there, you shouldn't be allowed to see what that student is eating because your 3D glasses will not allow you to see that stuff. However, the exact same thing is happening here, and in the terms of a schedule, you see it like that. You have 2 transactions, transaction 1 in blue, transaction 2 in red, and you see on the right to data object A in transaction 1, and then we read it here. The transaction 2 reads data object A, even though the commit comes afterwards, so the commit of transaction 1. So this is writing something to the database which isn't committed yet at the point in time when transaction 2 reads. So A reads, transaction 2 reads something that from the point of view of isolation is not visible, it's not even there. Yeah? So transaction 2 should only see stuff from committed transactions. However, it's reading a data object A which was written by transaction 1. Yeah? And that is called a dirty read. Later on, again, maybe I say it better here because it might confuse you. In the core lecture, we will say eventually, who cares? Because so what modern systems do, that's a different class of concurrency control algorithms, is to say, okay, actually what you're reading here is the committed version. Yeah, so a modern database system will operates on a versioned store, and that makes sure that even though you wrote to object A, so here the transaction, maybe I add this one here. Yeah, so basically what's written here is not the same, basically call it A prime if you wish. Yeah, so if transaction writes a new version to data object A, then still the other transaction here would be reading version A and not A prime that was just written. Yeah, that's done through a version store and leads to a class of algorithms that are called MVCC, multi-version concurrency control. Basically, all modern database systems use that versioned approach. For instance, Postgres is built on that, but basically all systems I'm aware of. Yeah. But to get there, we first have to assume that we don't have a version store, and that's what we're doing here. And that is really, in this world, we assume, yeah, no, here, this A that's written there, if that's written there, this transaction reads that modified A. So here we actually read A prime in this situation. If you write a new A, then you read the A prime, and that exactly is a dirty read. You read something that shouldn't have become visible because it wasn't committed yet. That is a dirty read. Yeah, then there's a non-repeatable read. That refers to the phenomenon that a transaction reads the same data object. Yeah, you have multiple read operations on the same data object. You see it here. Yeah, read on A within the same transaction. However, in between, the other transaction 2 writes a new version of A. Yeah, then commits. So this is, then you're reading it again, but now you're reading the new committed version of A. So this is not a dirty read. The second is not a dirty read. If you had here, if this were there, that would be a dirty read, also a non-repeatable read, but also a dirty read. But this read is not dirty. You're reading here you're reading a committed version of data object A. Here you're reading the committed version. However, it's non-repeatable in the sense you read different versions, which again is violating isolation, because from the point of view of the transaction, the assumption is I'm alone in Mensa. How can it be that I read it when the first time I read 42, and the second time it's 43. There must be someone else in Mensa. I'm not alone in Mensa, it seems like. Yeah? That is not allowed. Yeah? So whatever you read, the transaction should always read the same stuff. Yeah? Well, you have to pretend to the transaction that reads the same stuff. Reads the same stuff. Yeah? But if someone modifies it concurrently, we have to make sure that for transaction 1, it still will read the old stuff. Yeah? That's how we need to fix non-repeatable reads. Okay, and the third is cascading rollbacks. So that refers to the phenomenon of a transaction performing dirty reads and writing new values based on them. Yeah, so you need dirty reads for that. So you read some information from the database, and then you do some calculation in your application, and then you write something to the database. Your schedule, well, we see that as here. So transaction 1 writes data object A. Then transaction 2 reads that modified data object. Transaction 2 writes something somewhere, doesn't have to be A, it can be B. Yeah? And, but then transaction 1 aborts. So what does it mean? All or nothing. So this change to A was not persisted to the database following the ACID contract. Yeah? Because we have all or nothing, that means all changes transaction 1 did must be removed. Okay, but transaction 2 already read that stuff, the uncommitted stuff, and then wrote some other stuff potentially based on reading this. Yeah? So here again we have the problem that we don't know the application code. Yeah? So we get a SQL command that reads object A, and then in the application code in Django or whatnot, yeah, maybe something is done with that A that influences how B is changed. That happens here. So it doesn't mean it has to influence B. This read operation does not have, it's not necessarily influencing B, but it could be. We cannot exclude that. Therefore, this write is based potentially on this value, which never existed. A should, yeah, it existed for a short period of time, but from the point of view of isolation, it never existed. Yeah? Actually, again, T shouldn't have been able to read that modified object. Yeah? So that's a problem. That's a cascading rollback. And yeah, and then you can, why cascading? Because you can cascade transactions. Yeah? And that may lead to a cascade of transactions you have to roll back. Yeah? In other words, a cascade of transactions that have to be aborted, have to be undone. And that's what you're seeing here. So assume transaction 1 writes data object A, then transaction 2 kicks in, reads it, and potentially writes something to B, then transaction 3 reads the B and writes something to C. Now C is potentially influenced by this initial write. Yeah, now if transaction 1 aborts, you can get rid of, you have to remove all of these changes. Yeah? Have to be removed. So in other words, you have a cascade of transactions that are affected and have to be rolled back. That's why it's called a cascading rollback. So you don't want to have that. So I mean, these namings of these problems are very old. And I guess it's inspired by a real problem they had. Yeah? So if you think about that, this gets really, really bad if transaction 1 takes a long time until making a decision. Yeah, for instance, think about the user interaction. Think about that the UI opens a transaction and then waits for the user to hit save or hits commit eventually. Maybe the user gets a coffee in between and then only after a long time, oh no, I changed my mind. I'm not gonna save that. I say abort, yeah? Discard my changes, yeah? And then in the meantime, many transactions potentially ran, and that might lead to thousands of transactions to be that have to be rolled back. Yeah? So that's a problem you don't want to have. Okay, so how do we avoid this stuff? And yeah, there's a traditional way of avoiding that, and you might have seen that in other lectures, and that's based on locking. Yeah? So programming languages offer you to lock certain data elements, and what we lock here is tuples. Yeah? So by locking tuples, we can make sure that concurrent threads don't interfere with each other, or that we can control how they interfere with each other. And we will support we will discuss along the lines of 2 types of locks. One is a read lock and the other is a write lock. A read lock is also a shared lock because you can have multiple shared locks, multiple read locks on the same data object. So we have as abbreviation an R for read or S for share. It's the same thing, just a different letter. And for write locks, that's also called an exclusive lock, because if you want to write to a data object, there can only be one thread writing to any data object. So this is called an exclusive or X lock in the following. And so whenever you want to read something, you first have to acquire a read lock. If you want to write something, you first have to acquire a write lock on the respective tuples. So we are talking about locking tuples. That's a dimension you can make a decision on in a database. You can say, okay, I lock an attribute value of a tuple. Yeah? So you might allow for 2 threads changing different attribute values of the same tuple. That's a design decision, and that's typically not taken in database systems because the overheads are too high. People decided a long time ago, can be debated. But in most algorithms you see that people do locking based on the tuple granularity. Yeah, the tuple can be locked, but not the attribute value individually. And you could use other granules. For instance, SQLite had a much coarser granule. There's one writer on the database at all times. There you lock the entire database for writing for one of the threads. You could lock a specific table. You could lock a set of tuples. That's a locking granularity. For the moment, we assume it's per tuple. Okay. Yeah, and then, of course, if an operation doesn't receive a read or write lock, this operation must wait until it's allocated, until it gets the lock. All locks must be returned at the latest at the end of the transaction. Otherwise, you have locks that can never be acquired anymore, and so forth. So we denote a lock of a transaction Ti on data object AJ with get read lock. get read log for transaction I on data object AJ. Or we can also say get shared log, again it's the same thing, and the write log is within X log. And you have a release log operation. Yeah, now we can enter that to our schedules, but before doing so, we look at the compatibility matrix that basically defines which logs can be acquired in which situation. So for each tuple at any time, if no write log exists, any number of read logs are allowed. Yeah? An arbitrary number of read logs are allowed on any data item. If no read or write log exists, one write log is allowed. So the write log is really exclusive, meaning no other log must exist on the data object. Only if that is the case, you can acquire a write log. So basically, that leads to the following matrix. So if that is a log you're requesting, and that is a log that is existing, if you're requesting a shared log, yeah, if you're requesting a shared log and there's already a shared log, yeah, that's fine, you will get that other shared log. However, if there's already an exclusive log, you won't get anything. You don't get the shared log. If there's no log, you also get the shared log. That's fine. If you're requesting a write log or exclusive log and there's a shared log, no way, you don't get that. If there's an exclusive log, no way. So the only situation you will get an exclusive log is when there's no log already given out for that data object. So that's the compatibility matrix. Okay, and then we have to differentiate between short-term and long-term logs. They make a huge difference on the isolation guarantees you can give in this world. So as I said, now you want to read a data object, you want to write a data object. Before reading the object, you have to acquire a log. Before writing to the data object, you have to get a log. And that's what you see in the examples here. Here, for example, you want to read, but you first have to get the shared log on A. If you don't get the shared log, you halt the transaction. Yeah? So you basically here you will be stopped if you don't get the log. Maybe because there's an exclusive log already existing on A. Yeah, but once you get the log, you read the data object and then you release the log. So this is really a pattern, like immediately before reading, you acquire the log. And when you're done reading, you release the log. Now the same for writing. You see it in the example here. Immediately before writing to A, you acquire the exclusive log. Immediately afterwards, you release it again. And those logs are called short-term logs. So just for the very action of doing a single read and a single write, you get the log, release it. Get the log, release it. That's called short-term. Yeah? Oh, okay. Weit hier. Anybody hurt? Hurt myself. Okay. Long-term logs, in contrast, here you keep logs for longer than the actual read or write operation. And that leads to a protocol that's called two-phase locking, 2PL for short. So it looks in general something like this. You basically have two phases. So along the timeline you see we have this begin of a transaction and we have the commit of a transaction. We only look at one transaction here, not the interference of multiple transactions, it's just one transaction. Yeah? So we have a begin transaction and a commit transaction, and here you have the number of logs. And what that means is there's a growth phase. That's a phase here where the transaction is allowed to acquire logs. Then there's maybe a kind of a plateau phase. The transaction is doing some stuff but not acquiring logs and also not releasing logs. And then there's this shrinking phase where the transaction is returning its logs. Until eventually, of course, when committing, all logs must have been returned. That's part of the protocol. You cannot keep them forever. You must return all of your logs. Yeah? But there's growing and there's shrinking. And as soon as the transaction returns the first log, the shrinking phase begins implicitly, of course. Yeah? You start giving back a log, then you can't acquire another log anymore. Yeah? So you have to make up your mind before. And that's called the two-phase locking protocol. And then basically, if your transactions follow that protocol, you already can show that this ends up with something where your schedules are conflict serializable. So now we have an algorithm that does operation at a time Yeah, we don't look at all of the transactions in a batch and make a fancy theoretical argument to determine whether it's conflict serializable. No, now I have an algorithm. I'm saying, hey, if you organize your transactions in a way that they follow 2PL, you already have a conflict serializable schedule implicitly, even though you have operations coming in one at a time. And that's super cool and that's super helpful. And then you would say, yeah, we're done, right? No, we're not done, because in such a schedule you could also contain, there could be aborted transactions, yeah? So as shown before, the user can always say abort transaction, or due to some other reason, the database system may internally say, no, I abort the transaction, and then you're screwed. Then 2PL is not enough. That's not strong enough, this property. So it's important to keep in mind that conflict serializability only means that the schedule is equivalent to a serious schedule, but not that the transactions aborted in the schedule take back the introduced changes. So in other ways, look at it like that. So you can have a bunch of transactions, some of them committing, some of them aborting. Yeah, and then you have them all available in the batch. You do this analysis with the conflict operation, swap them through back and forth, eventually end up with a serial schedule. You know it's conflict serializable. Yeah, that's the easy case. Yeah, you have all the transactions with all the operations and you can make an informed decision. Now we are in the world where we have 2PL operations common at a time. Those transactions are firing operations. And yeah, we still know it's conflict serializable. However, we are violating ACID. If we only do two-phase locking, we are violating ACID like how? Which letter is violated? Ah, yeah, didn't see you.
Yeah, maybe again, isolation, we have these locks, and when we check for a lock and then see, oh, it's locked, then somebody else might now do something in this reader, right?
Mm-hmm.
Could be a point, but then this is the implementation of all locks.
Yeah, very good point. You could argue, even though the fact I need to acquire a lock gives me a hint, there must be someone else there. Yeah, you're in Mensa, and you feel like, why would I have to lock? There's no one else in Mensa. Why do you even have to call the method, right? Very good point. Very good. So isolation is more like, the concept applies more, so maybe more like down to the implementation level. Huh? And maybe the confusion here is that if you look at that, if you look at this slide, so this looks like something the user should do. So it looks like that you send a SQL statement and you should also send the log operations. No, 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 no. The system is going to do that, so you don't see that, and then maybe that answers your question. Yeah? A very good point. Very, very good remark, actually. Yeah? Where was I? Here. Yeah, but a very basic property of transactions I mentioned initially. So if you have a bunch of transactions, some of them are committing and aborting, it's conflict serializable under this theory, swap through, you have a serial schedule, blah, blah, blah. Now you have 2PL and says, that's fine because all follow 2PL, it's also conflict serializable. But what's the problem? We made durable actions of aborted transactions. We never revoked them. We executed all of them, no matter what, whether they were committed or aborted. Yeah, that's pretty bad. Yeah, you shouldn't do that. Yeah, so if it's aborted, again, the contract holds that none of the actions must have been applied to the database, so mustn't have become durable. And what I showed you initially, that also means no one else should have been able to read this stuff, dirty read, cascading, rollback, and stuff like that. Yeah? It shouldn't at no point become visible, have become visible. No one else should have seen this stuff. And that's not true here anymore. So 2PL doesn't solve this problem. So how do we solve that? So there's a couple of ideas in that space, and one is to make two-phase locking become more careful or more conservative or strict, as it was coined back then. And the idea is you don't have a shrinking phase anymore. Yeah, why not do it like that, okay, you just run 2PL in a way that there's only a growth phase, but there's no shrinking phase anymore. And only at the point of time when the transaction wants to commit, it returns all of its logs in an atomic operation again. Yeah? And this would prevent cascading rollbacks actually. Yeah? Why? Why would that prevent cascading rollbacks? No shrinking phase anymore. The logs are not returned only at an atomic point in time when the transaction commits. So what does that imply? How can a cascading rollback occur, or how can a dirty read occur? So we had these examples before, yeah?
When we return the log sequentially, another process could then take this log and start its plateau phase, so it tries to write
yes.
or read, and then we get these dirty reads.
Yes.
And if we do it at one point in time, the commit is done.
Exactly, that's the answer. So if you don't, I mean, why is there a dirty read? Because you read stuff, you read a change from another transaction that hasn't committed yet. Yeah, so if this transaction wants to modify something, it has to acquire an exclusive log. Yeah, now I'm saying that log is not going to be returned before the transaction commits. So no other transaction can pick up any log, cannot read this stuff. It won't require the log, it's impossible. No way you can read anything that's dirty, no way. And if you don't have dirty reads, you don't have cascading rollbacks. Yeah, that's basically the idea of it. I think I had a slide on that. Where's that slide? Didn't I have some? So here, that's this slide basically. Yeah. Yeah, that's basically this space that allows for deadlocks. Yeah? You return logs, even though the transaction is not done yet, you're returning logs, so the other transactions can pick up a log on those data items you potentially modified. Yeah, then you're in dirty read space. Yeah? And exactly that is fixed by strict 2PL. So that's, that problem is solved if you run it like that. Okay. So where was I? Right, okay. Yeah, and so with that you fix the dirty read problem and cascading rollbacks and non-repeatable read. But there are other problems that are still possible, and one is called the phantom problem. So what is a phantom problem? That's used to refer to the phenomenon of a transaction reading a set of tuples multiple times, say, reading a set of tuples in any where condition, where a equals 42. Yeah? So far we talked about a situation where we read single tuples. Yeah? If you recall the slides from last week, I had where I defined the R and the W, the read and the write operation. It was always with respect to a data item, and I said at most one tuple. That can be an attribute value, but I said no, the biggest thing you can read, the biggest thing you can write is a single tuple. That's what we said. Now we're looking at a bunch of tuples that are potentially read or modified by an operation, and that leads to what's called a phantom problem. And it's kind of similar in spirit to repeatable read. Repeatable read is with respect to a single data object, aka tuple. Yeah, so we read the same tuple within the same transaction and see different values. So it's a non-repeatable read. Yes, you want to have that as a repeatable read. And that can only happen because there was a dirty read. And the phantom problem now, however, is with respect to multiple tuples. Yeah, that could also be used in aggregation or stuff like that. So they're similar in spirit, where, however, repeatable read, single tuple, phantom problem, multiple tuples. So here's an example. So two transactions, one is selecting, it's just aggregating, computing the sum over all accounts. So what is the total money available in the bank here over all accounts? That's what this is doing. And that basically returns an integer, yeah, it's 2 digits maybe, yeah, so float. or fixed comma representation, some currency value, and that is assigned to variable x, maybe in your application code. Concurrently, someone creates an account, insert into accounts values 42, 5,000. So account number is 42 and has a balance of 5,000, does commit. Yeah? Now you run the same query here again. You compute the sum of all accounts and you get a sum that is by 5,000 higher than the x you read before. So it's kind of a repeatable read, however, on the tuple level. And the problem is that you do not catch that with the strict 2PL I introduced before. Why? I mean, we had 2PL, we had these long-term logs, right? Well, why isn't that fixed? Someone else? And you again, yeah?
At the point that we done balance for the first time, we take all the logs for the tuples.
Yeah.
But then this new account is created where we have not taken yet this log, so it can do its performance.
Yeah.
And it's basically excluded at the time point that we do our result for the first time and only the second time.
It doesn't exist at that point in time, right? Yeah, okay, yeah. Right, that's correct, yeah. So what we do is we log tuples. That's what I told you. We log tuples, and so basically here to run something like that from accounts means you have to log each and every tuple in the accounts relation. You have to get a shared log, a read log, for each and every tuple. If you get that, you run this stuff, you get a number, that's that. You're not committing yet, yeah? So you have all the read logs already. Following 2PL, you still keep those read logs. You're not giving them away. But now a new account is created with ID 42, and you don't have a log on that in transaction 1 because it didn't even exist at the point in time when transaction 1 started. Yeah? So there's no log on that. So this transaction 2 can insert it, can insert the tuple, commit it, everything is fine. Now you do the same thing again, and then the database system will understand, okay, I have to acquire the read log, maybe have to recheck whether I need other read logs. It will acquire the read log for the new account and compute a new sum. Yeah? So this is called, I mean, it looks like a repeatable read, a non-repeatable read. But in fact, it's called a phantom problem. Phantom because all of a sudden another tuple appears that wasn't there before. Yeah? It's like a phantom. You sometimes see it, you sometimes don't see it. And that's again violating the very idea of isolation that from the point of view of T1, no matter what, you shouldn't see any actions that were going on from concurrent transactions. Yeah? And that's violating that. That's called the phantom problem. And you don't have to necessarily, it's not only occurs through an insert, it's a classical example you will find in books. Through inserts you can actually do that with an update. Where's my update example? Here, this one. You can do that. We also had discussions in my group. But you can do that with an update, full stop. Yeah, so that's an example where you select the sum over all balances where the balance is greater than 900. Yeah? Everyone has at least something strictly greater than 900 as a balance is selected. And then you update concurrently in an account. You don't insert, you just update an existing account to have a balance of 1,500. Here we assume that account I'm updating, account number 8, previously had a balance that was 900 or smaller. So that's now all of a sudden a new tuple will be collected here. Now, all of a sudden this account number 8 is now selected in this where clause. The second time I execute that. That's also a phantom. Yeah? May happen. Also for delete, something may disappear that was there before, stuff like that. That's called the phantom problem. So if you look at this insert problem where a new tuple is created, here's another view of seeing the same schedule. So again, read operation on all existing tuples at that point in time. an insert operation adding a tuple to the set of tuples, and then again reading all the tuples that exist at that point in time. And another way of writing that down is something like that. Yeah? So basically, for all tuples in elements accounts, yeah, you do a read operation. Do the same thing here. However, here you're changing that set. Yeah? So you append a new tuple to the set, and therefore here, if this for all t will change, it will find another tuple that you didn't see before, and that violates I. So what does it mean for locking tuples? Well, there's not so much we can do about locking tuples at this point in time because the tuple simply doesn't exist at that point in time. It's more like that we have to get to a conceptual level here. We have to get away from locking tuples, but enter the world where we lock ranges of values through predicates. And that is the fix that is done in a database system that I showed here already. And this is called predicate locking. So to prevent a transaction with SQL statements that access multiple tuples from seeing a phantom, the corresponding value ranges must additionally be locked for such statements. Yeah? We can express this through predicates. We already have those predicates in SQL queries available already. For instance, if you do a select sum balance from accounts, this actually means you're selecting all tuples. Yeah? You're selecting where true. Yeah? Whatever the condition, I want to have all the tuples that qualify. So basically, this implicitly or conceptually locks the whole relation accounts before reading. In contrast, in something like that, here you only lock that part of the accounts where the tuples have a value greater than 900. And now here's a twist, and here's the important distinction. You can now, to determine what is locked, you can evaluate this condition and say, okay, at the point in time when I execute it, I look at all tuples that for which this holds true at that point in time. I mean, that's a very problem because we execute it now, we execute it 5 minutes later, that might return a different set of tuples. That's basically selecting tuples that qualify and then lock those tuples individually. It's basically like for each tuple in the set returned, get a read lock. That's basically what you're doing then. That's a tuple-based locking. But what we are doing now in the following is to say, no, the lock is already expressed here. The lock is expressed by the predicate saying, no matter what's going to happen in the future, I lock the range. No matter which tuple is in the range, no matter whether there's a tuple in the range, no matter whether future tuples are to be inserted into that range, I lock the range through a predicate. And that's called a predicate lock. Here's again an example to contrast the two. So by a predicate locking, we actually lock the data space where conflicts may occur. You lock a range in an attribute or a combination of attributes in a relation, whereas in tuple locking, you lock the data where conflicts may occur. Data meaning a data object, or in our word, a tuple. You only acquire locks on tuples, yeah? And that's a different thing. And that also means if you think about that, so for the ones watching the lecture in German, this slide is new. Huh? We had that before starting the lecture, did that this morning. Yeah, just inform your colleague directly, hey, come on, it's a slide, 22 is new, you really have to look at that one, right? Okay, so the example is we have the movies relation that's from IMDb, a little bit simplified, and then assume there is a tuple 42 Django Unchained 2012. So a lock on tuple M can actually be interpreted as a predicate lock on the data space. Yeah? Basically, this tuple is kind of saying, okay, in this three-dimensional space, yeah, basically now I'm saying, maybe no, this one. This is dimension 1. This is dimension 2, and this is dimension 3. Yeah, when you look back at the original definition of the relation where we had these three domains and then we had this cross product thing, my handwriting. get this cross product thing, D1, D2 cross D3, and then a relation is a subset of that stuff, right? That links back to that because we have 3 domains, but I could also equally call them dimensions. And basically this is a 3-dimensional point in that space. Yeah, and then express that either by saying, okay, those are the values, yeah, that's what I'm saying here, or I could say, no, I can express that as a predicate. So if that predicate is true, this means I hit exactly this tuple M. Yeah, all of these conditions are fulfilled in each of the 3 dimensions. Yeah? So this is a predicate here, and that is the tuple representation. Okay. Yeah, and then you can ponder about the compatibility of predicates logs. So there are easy cases, there are not so easy cases, but basically predicates will always help then if you have 2 transactions that have a predicate on the same attribute. So if you have let's go to an example before we enter this slide. Maybe which example could I abuse for that? What would be? Let's think about. How do I get a white? Also, maybe I can use my laptop for that. Maybe I think let's make that footnote because it's often is confused. So maybe let's scribble a little bit. So what I'm trying to tell you, there's we're talking about a geometric interpretation of these transactions. Yeah? And basically, how you can interpret that is let's assume you have a relation that only has 2 attributes, okay? And this is the x attribute, and that is the y attribute. Okay. Let's give them names. X, it's the x attribute. Y. So each relation, if a relation has k attributes, it basically defines a k-dimensional space, so to say. Yeah? And then you can define points in that k-dimensional space. Now let's assume that's a relation with 2 attributes. And now if you have a condition like, for instance, let's assume the condition is of the sort, what did I do? You have a condition like x equals 42. Yeah, something like that. Can you see it? You can see it. Then this is basically describing this a line in that geometric space. It's saying, okay, that is the values that qualify. No matter what the y data value is, I'm defining a line here, yeah, along the x dimension. And now if you have another condition like saying, yeah, y is actually whatever 12, maybe let's write it down here, that defines another line. So that's the geometric interpretation saying, okay, if that is 12, I can write it down here if you want. Yeah, so basically this is 42. So yeah, basically this is expressing in that 2-dimensional space. So those are all the y values having a 12 in the 2-dimensional space. Those are all the x values having a 42. Yeah, and where the both intersect, that is where my tuple 42, 12 lives, basically. Yeah, but what predicate logs do is they can make decisions if you have 2 transactions in the style. Maybe I copy this over. Assume you have assume you have a second transaction now. Maybe you have 2 transactions and one has a range like this, a predicate like that, and the other is a predicate like whatever, 32. Yeah, then okay, that is this other line, 32. So you have 2 lines which are parallel and can never intersect, so there cannot be a conflict. So that's the geometric interpretations. You know, we have these predicates on the same dimension and they exclude each other, then you have a problem. If you have a predicate like whatever, greater equal 32, okay, then this actually boils down to something like this. Then basically all the space to the right is defined by this interval 32, which obviously overlaps with this one here. Yeah, so both intersect along the x dimension, so that's a problem, that's a potential conflict. Yeah, that's the geometric world we're entering. So we are arguing along the lines of these high dimensional spaces. And the problem here is that if you go back to the initial example, now assume we have one transaction that has a condition on x and the other has a condition on y. You don't really know whether they have an intersection. Yeah? So what this y equals 12 actually means is y equals 12. So that's basically when I write down a predicate like that, if you see something like that in a where clause, where the where clause said y equals 12 with one equals a symbol, yeah, this is only halfway through because there's always some definition on all existing attributes as well in the table. So that would be y equals 12 and x whatever. Yeah, that's basically what this is saying, and that's what the line defines in the two-dimensional space. So the y value is fixed and x can be anything, but I don't know what it is. Yeah, and here's the same. This is actually saying x equals 42 and y whatever. Yeah, so this is a situation that could potentially have a conflict in this point. Yeah, so if you have predicate locks and one locking on that and the one locking on that, those locks are not compatible, as we say. They don't help you because you can still be screwed if you have a data item where y equals 12 and x equals 42. If you have a point sitting at the intersection, yeah, that's a potential conflict. Yeah, it could happen. You don't know whether you have that point. Yeah, if you don't have that point, that everything is fine. But if you have that point, you are screwed. Yeah, but as we don't know, yeah, so when looking at predicates, we don't look at the data. We just look at the data space. And if you just look at the data space, you cannot know whether this data item in the intersection exists. And that implies if you have selections like this on different dimensions of your table, yeah, those are not compatible, and that means there's a potential conflict, and then you cannot acquire the lock. Yeah. So basically, that is what this slide is saying here. In oh, I'm the wrong slide set. Okay, that's about the compatibility of predicate locks. So when are you allowed to get a predicate lock, and when are you not allowed to predicate lock? Yeah? And predicate locks basically help you if you have transactions on the same attribute, yeah, always selecting x equals 42, x equals 17, tra la 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 la, but if one selects on filters on x and the other selects on y, then you're screwed and they don't help you, and they could potentially be a conflict. Yeah, but these but if you log predicates and if you implement concurrency control to factor in those predicates for each and every query, you can actually avoid phantom problems. Where's my isolation stuff? So only way down below, okay. Right. So there's another problem we have to look at. That's the last problem in that space that can occur. And that's predicate-based locking. Not predicate-based locking, that's the deadlock problem. And that occurs in a situation like that. So you have two transactions, they acquire locks over cross. So basically what you see here is transaction 1 wants to get a lock on data object A. Then transaction 2 gets a lock on data object B. Now T1 is trying to acquire the same lock on B. It has to wait at this point in time. Okay, T2 continues, gets the lock on A. It has to wait at that point in time because A is holding the lock and also waiting. So that's a deadlock. None of the transactions can make any progress. Both are waiting for each other. And that's also something you have to handle in such a system. because if all your transactions log up, the system will not make any progress. So they will never continue. And there are a couple of fixes for that. One is also one is called conservative two-phase locking, C2PL or pre-claiming. Here the idea is you get rid of the growing phase completely. That means there's an atomic operation. So one of you asked back in the break, okay, but then so the question was, okay, if the commit means that you have to get back, that you have to return the logs one by one, how is that actually done? Because maybe the order might make a difference. You first give the first log back and then the other log back and the other transaction already kicks in. No, this is already done kind of as a transaction. Giving back the logs has to be done in a transaction itself. It's kind of transaction inception. Yeah? The metadata has to be returned in a transaction as well, or it has to be serialized somehow to avoid that at commit time you already gave back some of the logs and then the other transaction is allowed to pick them up. No, first all of them have to be returned. The commit has to go through, has to be valid, and then the other transactions are allowed to pick up those logs. It's very important. Yeah, and right, and the mirrored version of this approach of strict 2PL, yeah, where strict 2PL would be we still have a growth phase, but now we also kill the growth phase and say, no, when running a transaction, there's an atomic operation where you have to get all the logs that are required to run the transaction. Yeah, and that doesn't work. It's theoretically an approach you might come up with, but the problem is then you have to know which data items are to be touched at the beginning of the transaction. And that typically doesn't work because part of the job of a transaction is typically to find out what are the data items I'm interested in. Yeah, so it's part of a query of a transaction. So only after a certain time in the transaction you typically know, okay, what is affected, and that conflicts with these conservative approaches. So this is not done. So here's an overview again of the different 2PL variants. So this is a textbook stuff that creates conflict serializable schedules but has problems with dirty reads and deadlocks. Now then we extended it to strict 2PL where we get rid of the deadlocks because we only return the logs at commit time or abort time, of course, if you abort. And then there's this conservative pre-claiming approach where you basically have to know from the get-go what are the logs you acquire or not, which is basically not feasible. Yeah, so here's an example for pre-claiming why that is a bad idea. So this is how your code could look like in your application server. So you will do a begin transaction, a commit, and there's somehow is a condition which selects based on some variable which tuples are to be read. It depends on that, yeah. And then basically you either run that or you either run this one. Yeah, so only at this point in time, while running the transaction, you know what needs to be read. Of course, then you could say, okay, I analyze my transaction and I pre-claim all of this stuff. Yeah, but that brings down performance again because you're over-claiming. You're getting too many logs. That's also a problem of these different approaches. Yeah, you can try to acquire logs like crazy, but you should only acquire those logs you actually need. If you acquire logs you never need, I mean, that's kind of ruining the day of another transaction. Yeah? That's not what you should be doing. So I'm just mentioning this idea for completeness, but typically this doesn't make too much sense. Okay. Now, another common technique you see all over the place in databases, operating systems, distributed systems is what's called a wait for graph. And that's very similar to what we already had last time because it's the same thing as in this conflict graphs. So basically you do a vertex, a node for each transaction, and the set of edges basically now not define a conflict operation, but define whether there is a log held by transaction Tj, Ti is waiting for. So if Ti is waiting for a log that is held by Tj, you make an edge in the graph. That's called a waits for graph. And then you can show that if you have cycles in the wait for graph, that there's a deadlock. For instance, here in that example, that's a graph with 3 transactions, and T2 is waiting for T1, T1 is waiting for T2, so this is a cycle in the graph, so that's a deadlock. So what do? You have to transform the graph into a graph that doesn't have cycles. How do you do that? You kill some of the transactions. That's the job not of a database administrator, but of the database system. So the database system can analyze the graph and say, okay, I either kill T1 or T2. In this example, you're killing T2, and then you end up with this graph, doesn't have cycles, can be run, okay. Yeah? And then basically, I mean, there are 2 ways how you can do that, or handle it to the outside. The database system might simply halt T2 internally, and run this one, run these transactions first, and then try to re-execute T2. But the other way to say is to say, okay, it simply aborts T2, and then the user gets the signal, oh, your transaction was aborted, please re-execute it again. Yeah, that's a typical way of doing that. Yeah, but that's how you can resolve deadlocks, by using such a graph. Okay, so I think we're almost there. One warning here, if you read about this stuff in literature, on the internet, there's conflicting terms. There's conflict serializable and there's serializable. We'll also see that in the following slides where that makes a difference. So again, conflict serializable is with regard to whether it can be mapped to a serial schedule. But conflict serializable doesn't mean serializable in the sense people typically talk about serializable. And that's basically what we had half an hour ago already, where I said, yeah, conflict serializable is nice, but if some of the transactions do not commit, that changes mustn't become persistent in the database. So that would violate serializability. Serializability is a stronger term that basically is at the core of the I letter in ACID, saying if it's isolation, it's perfect isolation. No matter how you execute the transactions, nothing will go wrong. And conflict serializable does not imply serializability in that sense. So serializability is basically saying perfect isolation, no matter what happens. And that's our goal. And this term basically is used to signal that if someone says, yeah, that's serializable, he or she is trying to say, isolation is respected. But that's not implied by conflict serializable. So serializable, perfect isolation, as I just said. But in discussions, you will see that this is sometimes used synonymous as a synonym for conflict serializable. So you have to be careful. If someone says serializable, ask back what he or she means. Or it's used as a so-called isolation level. It's perfect isolation. In other words, it's also a perfect isolation. I didn't explain isolation level. It's used for perfect isolation, as just explained. It also has the 2 meanings of serializable. So just be careful of somewhere written serializable or someone says serializable. If in doubt, ask back. Okay, and that brings me to isolation levels. And if you understand this, you really understand concurrency control. So the idea of isolation levels is, and what people found out when they implement concurrency control is, okay, now we have this isolation implemented perfectly. We have perfect isolation. And we make that possible through running strict 2PL, through predicate logs, through these weights for graph. Yeah? But it turned out that these algorithms were quite expensive. Yeah? So they limited the number of transactions you could run in a database system. So people thought about ideas, okay, how could we get more performance out of the database system? What would be the right way of doing that? And what they decided upon back then was to say, okay, maybe phantom problems for some applications is not so important. Who cares, right? Maybe we give the database administrator the power to trade isolation for performance. So to make weaker isolation guarantees than ACID would require, yeah, if the people know what they were doing. So the assumption here is that, okay, maybe also a little bit, if you go back to this initial example we had last time, it was the pedals, yeah? Maybe if you go back, I think that's a good, this comes to my mind. What was that? I think early on somewhere. Here's this one, where I said, okay, a little bit like that. So rather than giving the customer four pedals for braking, you would say, okay, maybe we give them 1.5, or we give them 2. I mean, maybe they can handle this kind of situation, so we give them more power. So they will be able to handle situations, maybe they will be able to drive faster, to brake faster, if they know how to use those pedals. However, it could also be that in certain situations they will fail miserably because they're overwhelmed by what's going on. And that's the same, that is the spirit people had in mind here. So it said, okay, ACID is nice, yeah, these database professors, they want to have perfect isolation, but in reality it's too slow, so let's weaken the isolation guarantees, give the users a tuning knob where they can weaken the isolation level. Yeah, so, and that is the reason why almost all database systems allow you to tweak with tweak isolation, to have a weaker isolation level. And that is what the following slides are about. Yeah, this is a trade-off here again in this box. So the gain is higher performance due to less overhead for concurrency control. The loss is weaker isolation guarantees, which depending on the application can lead to isolation problems. So if you make a decision, okay, I'm fine with a weaker isolation level, yeah, because I'm so smart that I understand all of my queries and all my transactions. I know nothing is going to happen. The next day an application developer comes up with a query that ruins isolation and you're screwed. So it's a very sensitive, a very risky tuning knob to change. And my recommendation is don't change it from serializable. Yeah? Keep it also to the highest level. However, the problem is if you install a database system, for instance Postgres, this knob is not set to the highest level. It's set already to a compromise. Yes, you have to be really careful when using database systems to first check, oh, is it already set to serializable? Because these days you typically don't want to trade isolation with performance. It's kind of an historic decision people took at the time, and it's understandable that they took it at that time. The hardware was different, but these days it's rarely the case that you want to trade in isolation for performance. You don't have to do that anymore, I would claim. So you have to be a bit careful for using a database system. What is the default isolation level? And this is how this could be realized. This is an old way of realizing it, but that maps back to the techniques I presented here in class. So basically, this is the strongest level, perfect isolation, and this is the weakest level, read uncommitted. Read uncommitted means with respect to read operations, you do not acquire any log. You don't respect any logs from other people. You just don't care. When there's a data object, you read it. Who cares, right? With respect to writes, you still follow strict 2PL. So for writing, you always have to get a strict 2PL log in your transaction. And then you can show that in this world you still have dirty reads. I mean, of course, if you don't respect reads for anything that's being written, you have dirty reads, you have cascading rollbacks. In this next stronger isolation level, read committed, you make sure that you only read committed data. And that is the only change here. Now you acquire short-term logs. As write operations still follow strict 2PL, and never return their logs, this means you won't get a read log, not even a short-term log on something that's currently being written by another transaction. There's no way of doing that, because the other transaction must have committed. So that will exclude like that, you don't get. No, you have to be careful how to read the table. Yes, you don't have dirty reads, you don't have cascading rollbacks, but you still have non-repeatable reads. Yeah, because if you get away the lock, another transaction gets in concurrently, changes the item again, you get the short-term lock, you read a different version, just like on the slide that we had. Next level is repeatable read. Here you use strict 2PL for both reads and writes. So that's the tuple locking stuff I explained. Yeah, you lock all kinds of tuples respecting to strict 2PL, everything is fine. However, you still have phantoms. Yeah? And if you want to get rid of phantoms, you have to also use predicate locking, and then you don't have any of those isolation problems anymore. Yeah? That's an example of realizing that. And then there's a command for that, where you can set the isolation level per transaction, but also globally. That's how it looks like, and then you see these levels. Yeah. And the default in Postgres is read committed actually. Yeah, so the not the weakest level, but the second weakest level basically. What's the time? Let me check. Maybe we focus a little bit. Yeah, that's again a little bit this trade you're doing. If you do not log data objects and predicates, you get any number of problems. Yeah, that's the read uncommit level. Other transactions never have to wait. You have excellent performance. However, you might be screwing isolation. Where in contrast, if you're very restrictive on locking, you're ruining performance, yeah, but you don't get these isolation problems. And if in doubt, always use this one. Yeah? It's not worth risking an isolation problem just for some better performance. Functional correctness is always more important and must be respected. Yeah, we have a notebook on that, but I think you can take a look at that if you want, but I don't have time for that. Because I want to wrap up by mapping these things back to the examples we had initially. So question one was, how do we allow for concurrent modification of data without creating erroneous data? Yeah, concurrency control is the answer. How do we design that so that the process and the resulting of our system are efficient? For instance, through strict 2PL with predicate locks as explained here, or then the weakened isolation levels. Modern database systems use MVCC, as already mentioned, and it's also worth mentioning that the isolation levels may look very differently. So it's not necessarily how it is on the slide. So it gets a bit complicated if you really run a database system. They might have different concurrency control implementations. The isolation levels may mean different things. They're sometimes only there for historic reasons. If in doubt, just set it to serializable. If you have performance problems, don't solve them by weakening isolation. Don't do it. Not in 2024 anymore. Doesn't make sense. No? It's more like an historic tuning knob. It shouldn't be changed. Okay, so a little bit to the back to our money withdrawal example now with all the locks we learned about and mapping that to isolation levels. Assume we withdraw money in the bank with read committed. So how would that look like? Read committed meaning you get a short-term read log for transaction 1. Looks if there's enough money in the account only if balance is greater than requested amount the money should be withdrawn. It returns the read log immediately afterwards. T2 gets the short-term read log, looks if there's enough money, same thing here, returns the read log. T2 gets the long-term write log, reduces the balance and commits. T1 does the same thing. So that's a lost change because transaction overrides the change done by T2 here in this example. Consistency is not violated. However, for the simple withdrawal scenario, this is not sufficient. Yeah? So if you're withdrawing from one account concurrently, that's not going to work because you're losing an update here. So if you do that with read committed, That's a schedule representation of that. Yeah, that's the logs again represented. I inserted them into this visualization. So here's a read operation on this account 2, and there's a acquire log and a release log. So this is a short-term log. The read operation is wrapped in a short-term log, and the same happens here. Both read 100 current balance, and then here we do the check. Oh, it's greater than 100, then I can reduce it. Yeah, I can withdraw 100. I want to withdraw $100. So is there $100 on that account? Yeah, then I can execute the write operation. The same is happening here. Yeah. Yeah, and it overwrites the change done here, and that's what's called a lost update. Whereas if you think about that in a serial execution of those transactions, yeah, so basically, before the state is something like that, the balance is 100, and the state afterwards is 0, even though we got $200 out of the system. So here we write the new account, assume the account before was 100. Now we remove, withdraw 100. Now we write 0. Here again, we write the 0. Rather than checking the current account again, which is 0, removing 100 and writing -100, which would have been correct. It's not happening here. Yeah? So what should have happened in a serial execution should have been this. T1 is executed. Yeah? You can withdraw 100, but then T2 is aborted. Or the other way around, T2 is executed, writes a 0 as a new balance, and then T1 is aborted. Those are both two valid ways of executing these transactions, but not what's happening here, because the ATM will give out $200, but will only remove $100 from the account. So that wouldn't be correct. So if you do that with repeatable read, you get a deadlock in this example. So you see it here. You get a read log, which is not returned. So that's a long-term log. Here you also get a read log. There's only one read log on that account K2, so you get a second log. That's fine. Then you want to write to the account. This is also called an escalating a log. That's a special case. So you already have a read log. Strictly following the conflict matrix, you're not allowed to get the log. But as you already have a read log, you can acquire a write log on the same object, and that basically it's called escalating a log. Yeah, getting a log of a higher value, so to say. You still have to respect the conflict matrix, so there mustn't be any other log, of course. But at that point in time, already you have a deadlock with this, of course. And here's the same thing. Here you would have a deadlock with the other one, so the transactions are deadlocked. It doesn't work. Here's an example where you create an account with repeatable read. And that maps to the phantom problem, of course. So here you select all the accounts that have this zip number. So yeah, I assume there's a column zip here in the accounts table now. And I want to have the average interest rate. And then basically I update all accounts where that holds. So I first read the stuff and then I do an update, but it's the same condition as above. In between, I'm inserting something here. And then if you look about the serial executions, again, you first execute T1 and then T2, or first T2 and then T1. You either end up in this state or in that state. However, if I execute it like that, you insert in this state. Yeah, and that violates isolation again. So we have to do something about that. And that must be done here to fix that with serializable. Yeah? So again, as you have a situation where tuples are inserted, so the tuple logs don't really kick in. So we have to have range logs, aka predicate logs, to fix that scenario. Okay, so I'm running out of time here. Okay, maybe just to wrap up, I use just one thing I want to make you aware of. So when you conflict university with reality, so we looked at, for this case, at read committed. So that's not strong enough. If the read locks are only held for a short time, write locks can be issued that allow to change both accounts. For a repeatable read, it's then okay. The read locks are held until the end of the transaction. This means that other transactions may not be granted write locks. Concurrent writing becomes impossible for the other transaction, T2, but the deadlock is created. Then you could also set it to serializable and assume that no problems may occur in a situation like that. So here we have a situation where we read two values, both read the same values. So this is a situation where you read two accounts and then you make a decision based on the sum of the accounts. So you say, okay, if the sum of both accounts are greater or equal 100, then you can withdraw from K2, from account number 2. And you do the same in the other transaction, however, you write to different values. Here you write to K2, here you write to K7, but it's the same idea. This is withdrawing from account 2, this is withdrawing from account 7. Based on the same condition, so dear customer, you can withdraw money from any of your accounts as long as the sum over your two accounts is greater or equal 100. That's fine. That's basically what these transactions are doing. And from what I just said, yeah, that should be fine. However, there is one system that's infamous for that will allow that schedule. So that's also something you want to be aware of because what you should end up with is, again, this state or that state. So again, should be equivalent to a serial execution, first T1, T2 aborted, first T2, T1 aborted. But what that system would end up with is this state, which is illegal. And from what you learned in my class, you should now keep in your head, aha, Professor Dittrich said, if it's serializable, everything is fine, unless you're using Oracle, okay? Which happens to be one of the most expensive database systems out there. Yeah? So paying a lot of money doesn't mean that you get rid of all of the problems and get. Oracle is a great query optimizer and tons of features. It's insane, but they're not fixing this bug. I think it has been found 15 years ago, and when it was found, all vendors fixed it, but not Oracle. Yeah? So the scheduler I showed you will go through and will end up in an invalid state, will violate isolation, and we will actually revisit that problem again in the core lecture, just to keep that in mind. So the Oracle argumentation is somehow like, it's just such a corner case, who cares, and we want to be downward compatible. I don't know, I don't understand it, whatever. Yeah? So if you buy Oracle, you have an isolation level that's called serializable, however, it's not. Yeah? It's some slightly weaker than that. Okay, to sum up. So concurrency control is awesome. I mean, I know there's a lot of material and you have to digest many things, yeah. But again, the core idea is you get rid of having to fiddle with threading and concurrency control yourself, because you can delegate most of the things to the database system. And this is just awesome. It avoids so much work and pain for developers. Yeah? This is, yeah. Maybe you click on this link. I can't do it here, otherwise I get a copyright violation on YouTube. Yeah? Check it out, it's a cool video by a colleague professor from Berkeley. Isolation. Most database systems guarantee atomicity and isolation for transactions. Concurrent executions of transactions increases the performance of these systems enormously without creating any problems. Be careful with isolation levels. They're sometimes difficult to interpret. If in doubt, always use a stronger isolation level. Always check which isolation level is set by default and what this actually means in the used database system. If you have a system, if you develop an application that sends transactions and you want to make sure that isolation is guaranteed, check out whether the isolation level is serializable. If not, set it there and then you're good to go. Okay, so this is a cheat sheet here. I think you can read that back home. Further material, you can also read it back in German in the Kemper and Eichler book. Also the Al-Masri Nawate is available in German and English. That's it for today. Next week we will do, I will tell you something about data in the wild. So this is again contrasting what you learned here at university versus how people actually manage data in reality. It's quite interesting to see the difference. Yeah? See you then.